Global Max Plan plus qu'un moteur de recherche.
Hello, everyone, and thank you, Patrick, for invitation, and thank you, Steve, for being host, and thank you, everybody. I want to share my screen first of all. I think to share the just a minute. Let me see. I don't know why it's not showing the present. I want to share my screen, but it doesn't let me. I don't know why. Oh, can you see my screen? Can you see? It's written the beauty of mathematics. Do you see that?
Yes, we can see your screen. Yeah.
Perfect. So before diving into the research I'm going to do, which I'm going to share with you what is my research about, I wanted to share with you the sentence. It was very uh, helpful for me. The beauty of mathematics only shows itself to more patient followers. So it was a lot of time I wanted to give up, and this sentence helped me to do one more step, be more patient, and this was the reason I wanted to share with you. I think everybody needs that. And before starting that, I want to say Durud Bar Iran is because I'm from Iran and these days Iran situation is not well. So I wanted to say Durud Bar Iran, which means salute to Iran. Okay, let's go to the topic I'm going to talk about. The title is Construction of Universal Vector for Composition Operators on the Complex Plane. And this is the research and dissertation I was doing. I will start with the definition. What do I mean by universal vectors? Which operators we are working? What is the space I'm working with? Then I will go through the history. Then after the history, the motivation. Then we will dive into what I found. And if we had time, we can go through the correlates and theorems we found. Anytime you had any question, feel free to stop me. So first of all, we consider the space X be separable, metrizable topological space, and we want to define universality for a sequence of operator Tn from X to X. So it's like we have T1. Oh, so what I want to define, the property of universality I'm going to define is going to be for a sequence of operator. So T1 is from X to X, T2 is another operator, again from X to X. All of them, they are going to be continuous and linear operator. T3, X to X. Now I'm going to talk about this sequence of operator has we call them universal. They have, if you look at the universality as a property, we call this sequence is universal if we have the following. Okay. Okay. So a sequence of operator Tn is said to be universal if there exists an element x belongs to x such that the set Tn of x n greater than equal 1, this set B tends in the space x. So this here you can see based on the way we are defining the universality, so we need X to be separable. By separable, we mean it has a countable subset which is dense in the space X. So let me explain a little more about what do I mean by universality. I think I have, oh, I don't have any space. Okay. So this is the space I showed you. We had a sequence of T1, T2, T3 to the end, and this is the space X. So imagine this is X. I just want to give you intuition about what is happening. So all TIs, all the operator we have T1, T2, T3, all of them, they are from X to X. And what we are looking for, because all of them, they are from X to X, so let me to delete one of them. And I just show uh, both on the X. So I'm looking for an initial point. Okay. For example, a small X here. I'm looking for an initial point like x here. This is a small x, this is the capital X, which is showing the space, or I can show by f. So I'm looking for this a small point on the space that after applying t1 of x, for example, imagine t1 of x is gonna be here. Maybe t2 of x is going to be here. Maybe t10 of x gonna be here. So I want to find that x, which after applying tn of x, I can get close to any point in the space. So which means if I pick a point x in the space x, now we can go to the next. Okay, what do I mean by that? If here is x, this is the space x. Let me show by capital X. And here is the point x we are looking for that. If the sequence t and the sequence of operator are universal, it means I can find the point x, the small x here, that if I pick any other point on the space, let's call another point like y. If I pick any other point like y in the space x, so let me write here, pick y. I can find the sequence of t and of x that they are very close to y. I can find the sequence, for example, I don't know, t maybe t 100 of x, t 200 of x. We can find the sequence of t and of x that they are getting very close to the y. In other case, when we say a set is dense in the space x, it means there exists a subsequence of tn, which you can show t and k. So if we pick any arbitrary point y in the x, there exists a subsequence. We can show the subsequence by t and k, which means just a subsequence. For example, from t1, t2, t3, maybe the subsequence gonna be t2, t4, t6, any kind of subsequence, but there exists a subsequence t and k such that there's t and k of x approaching to y. Can I continue? Any question? Let me just see if is it okay if I continue? If you have any question, feel free to stop me. Okay. So now here I'm telling t and k of x. Is there any question? Okay. I'm telling t and k of x approaching to y, so I have to share more information about what is the space x and what is the topology on the space x. I don't go to universality. Let me go here. The space I'm working on my research is going to be the space of analytic functions, h of c. So the space h of c is the space of the functions. Here, so h of c is the space of all functions f from c to c, where f is analytic. And when the functions are analytic, it means they are differentiable, even they have the first derivative, the second derivative, the third derivative, they are infinitely many differentiable, they are continuous, they are very nice operators. So all of the space I'm working with, I have the elements, the vectors of Maya space, they are operator from C to C, which they are analytic on C, and analytic on C, we call them entire function. So if you here I use entire, it means analytic on C. So this is the space I'm going to work on that at the end. And so I have to say, what is the topology of this space? So the topology we are working, we call that the compact open topology, the topology on the compact sets. When we are working on the space of h of c, when we want to say if n approaches to f, we mean if we pick any compact subset of c if n approaches to f uniformly on that compact set. So it's different, it will be different like that. If a sequence of fk converges to f in h of c, if and only if for any compact sets k, we have the following. So here we define the sup norm as following: sup of fn of z minus f of z, z belongs to k, this goes to 0 as n goes to infinity. So anytime I'm saying fn approaches to f, I mean this is going to 0 on compact subset of C. For any compact sets, we have the following. Can I continue? Okay. So let's go to the history before sharing my result. So the first thing it was, first people was working in this area. It was Birchhoff. Birchhoff was working on the hypercyclicity. Hypercyclicity is a special case of universality. I skipped that and I can go top to share with you. So in the universality, we say we have a sequence of operator. Let me write it here. Okay, here. Oh, just ignore this y, it shouldn't be here. So universality, we talk about a sequence of t and n greater than equal 1 or 0, and all of them, they are continuous functions, continuous linear operator, and each tn, they are all on the same space x from x to x, where we said x is separable, metrizable topological space. So now we said tn is universal, the sequence tn is universal if there exists x, the small x belongs to x, such that tn of x n greater than equal 0, this be dense in this space. So this is t1 of x. Oh, sorry, I should by t0. t0 of x, t1 of x, t2 of x to the n. This space in this space. This be dense in the space x, which we said it means if I pick any element in x, I can get close to that vector in x arbitrarily enough. Very, very close. I can get close to any element in the space X. Now, this was for universality, and now I want to say hypercyclicity. So hypercyclicity is a special case of universality, but this time, instead of working with the sequence of operator T1, T2, T3, I'm going to have just a single operator. So this gonna be hypercyclicity. I'm going to write it here. This was universality. So for hypercyclicity, this time we are working with a single operator, t. This is again continuous and linear, and t from x to x. And this time, instead of tn, we are working t to the n. Composition of t by itself. So t2 of x is gonna be t of x. So in this case, we will say t is hypercyclic. Again, if there exists, but let me write more details. I'm sorry if my handwriting is not nice. This time we have t to the n of x, n greater than equal 0, this be dense in the space. So this time t0, we consider t0 as just x. I can write it, doesn't matter, but let me just write t0 of x. It's gonna be defined the identity t to the 0, t2 of t1 of x, t2 of x, this be dense in the space x. So hypercyclicity is a special case of universality, and the first research is like we are extending hypercyclicity. So the first person was working on that in 1929. Birchhoff showed that the a translation operator is hypercyclic, and he construct an entire function that was a hypercyclic vector for T1. So he showed that here T1 of f of z is f of z plus 1 to find to just make more sense. So if I combine it by itself, it's gonna be T1 to the 2 of f of z. So it's gonna be T1 of f of z plus 1. It's gonna be f of z plus 2. And so for T1 to the n of f of z, it's gonna be f of z plus n. Okay. Then he showed that this h of z, so if we just imagine this gonna be h of z, the space of analytic functions on C to the C. He showed that so there exists a hypercyclic vector. So I can't even use universal because hypercyclicity is a special case of universal. So if I made any mistake, it doesn't make a big difference. So he showed that there exists a hypercyclic vector like f that if I apply Tn of f, so show that T1 to the n, oh sorry, T1 to the n of f such that T1 to the n of f n greater than equal 1 is dense in h of c. It's like after applying T, for example, T1 is gonna be somewhere T2, T3, T4 at the end. It's gonna get close, move around in the space, and get close to any point in the space we have. So Birkhoff showed that the translation operator T1 of f, which is f of z plus 1, is hypercyclic. And then MacLane showed that the differentiation operator is hypercyclic. And Godefroy and Shapiro combined their result and showed that every continuous non-scalar linear operator L that commute with the differentiation, this is the differentiation operator, is hypercyclic. So now if you look at this, if I want to say an example of an operator that commutes with the derivatives, you can see if I define L to be T1, as we defined just before, from H of C to H of C, where T1 of f of z is f of z plus 1. There's going to be this actually the operator they are talking about is even covering the operator which Birchhoff was talking about. Because as you see, you can see L of this is continuous, non-scalar linear, and you can see T1 of D of f of z. This is T1, D is derivative of prime of z. Then it's going to be f prime of z plus 1. And in the other hand, I show with different colors on the top. If you look at D, you're going to be the rest of that. D of T1 of f of z is going to be D of f of z plus 1. It's going to be f prime of z plus 1. So I want to say what they showed that it was more general, and what Birchhoff was proved, it was like a special case of what they mentioned here. And then Bernal and Montens, they showed and they actually proved this, that any composition operator where the symbols, I call sigma and symbols anytime I'm calling symbols. where the symbols have the form a and z plus bn, is universal if and only if lim sup of minimum of absolute value of bn and bn over an is infinite. This was what I got interested about it. This is even the question I'm going to work on my dissertation. I worked, not I'm going to work, it's done almost. So what they show that, but their proof, they showed any composition operator. So they are working with the composition operator on the space of entire function. They showed this sequence is universal under this condition, but their proof was not constructive. It was existence. They proved that in the way of, by the way of contradiction, they showed, okay, under these conditions, we have universality, and anytime we have universality, we will have this. So their proof was existence. It wasn't construct. Uh, they didn't use the constructive method. And the other thing was interesting. They showed that even the sequence of universal element is dense in the space. And it's interesting, we say they are dense in the space. So it means if we get any point, if we pick any point in the space, we can get close to that by a universal vector, but it's gonna be tough to point out how does it look like. It was something interesting for me. So what they show that the composition operator is defining like the following. So we have this time the sigma n is going to be the sequence coming from the conformal automorphisms of C. By this we mean all the sigma n are from C to the C, and sigma n has the form A and Z plus Bn and is holomorphic, and even its inverse is holomorphic. They are holomorphic, or just here because we are working on the complex plane. Holomorphic and analytic are the same holomorphic, and its inverse is holomorphic. Oh, sorry. Okay, any question? Okay, so I will be happy if someone help me. So Patrick, can you help me with, I have a question to ask you because I feel I'm alone here. Are you there,
A
Patrick?
Yes.
question?
Good. So, Patrick, based on the condition I put here, can you give me an example of the universal, an example which satisfies IMP and following and is universal?
Um. Okay. So let's say z plus n.
Yeah, thank you. Yeah, perfect. So for example, sigma n of z, z plus n, as you see, bn is n is going to infinite, and bn over an, because n is constant one, so it's going to infinite. So therefore, the operator Patrick made here, so the operator we can make with this, c sigma n from h of c to h of c, it is universal. So, which we mean there exists for sure, we can find f belongs to h of c, such that uh, this set c sigma 1 of f, let me write from there. It's gonna be a big set. C sigma 1 of f, c sigma 2 of f, to the n, that's gonna be dense. And c sigma 1 of f is f of z plus 1, because n is 1 is going to be z plus 1, f of c sigma 2, f of z plus 2, and c sigma n going to be f of z plus n. That's going to be dense in the space of h of c. So let me ask, thank you, Patrick.
Very welcome.
Let me
Yeah,
ask someone
and
else.
and usually we don't ask questions throughout the talk. Like we usually ask questions at the very end. So if you feel like you are alone, you are actually not. Okay, because we are
Is
not.
that okay to ask in the middle of talk or it's better
Yeah,
to
yeah, yeah. I think it's very okay to ask in the middle of the talk, but we are
that's
not.
yeah,
Like,
because I will feel I'm alone there then if I don't ask questions. I will ask someone else then another question. So let me. Steve, can you help me with the other question? Steve, can you give me another example of composition operators which gonna be universal? Is it Steve there?
yeah. So basically, you want this condition to be satisfied, right? Bn
Yeah.
goes to infinity, and Bn divided by An goes to infinity as well.
Yeah, so we want to see what should we choose for AN and what should we choose for BN. Just
Mhm, mhm. Okay, let's start with Bn. Okay, let's just choose something that goes to infinity first. Bn.
Can't you exponential n from the n?
oh, good. So your Romek, what should I put for AN?
N
N, perfect. And what should I put for BN?
exponential n.
E to the N, you mean? That's
See,
Yes.
thank you. Yeah. So as we see here again, Bn over An is going for to infinite for sure, and Bn is going to infinite. Thank you very much. Thank you. Yeah, so it's easy. The only thing we have to check is just satisfying these two conditions. If it satisfies these two conditions, so this composition operator gonna be universal. Thank you, everybody. So then, and Heinz showed that their proof. Oh, sorry. Yep.
I think that Anifa has have it. Anifa, you have a question.
Yes, yes. Thank you, Salma. I wanted to know if there are some case where we know exactly X made this.
I couldn't hear your
Okay,
voice
in the
completely.
theorem we say that in the theorem we say that the space is universal if there exists S such that we have the condition that satisfy. I wanted to know if in for instance the two cases that you present in the slide before this.
A slide before
I
this.
wanted to know if
You,
yes. I wanted to know if we know exactly what is the X that what is the X, yes, that satisfies this condition.
that is very good question. And that was my question too, Aniva. It was the reason I worked on that. So, the most of them, they don't know what is exactly the X. They just know, they just can show there exists an X. If there is an X that satisfies this, then it's gonna be universal. But the way they show there exists such X, they use the property of the functions they have and the space they have. But they don't know what is this X exactly. But these days, some of them they are working to know what kind of X do we have. So can X has, for example, can X be as infinite product or can X has the following form? This is something we are working on that. What is exactly X?
Okay,
Did
thank
I,
you.
did I answer your question?
Thank you.
Welcome.
Yes,
So this is very good question. This is a question that's gonna be, and this is an ongoing research. So, for example, you can come with this question. If I define can X have the following form, and then see or under which condition I can have an X which has the following form. For example, define for yourself a form. And this is the question we were curious about to see what is the form of X. For example, this was our motivation. Seidel and Walsh, they showed that the composition operator on the space of analytic function on D is universal. And Heinz, who was I think he was the student of Walsh, he showed that the composition operator on closure of Bolovich infinite of D this sequence is universal, even has the universal element which has the form of biological product. So in 1954, Heinz could show the universal element has the following form, the form here. And then we had this question, okay, so for our case, can we talk about, can we say we always have this form, or can we simplify that? Then Chan, Hofstad, and Walmsley, they showed that the vector, the operator we were talking about, the non-scalar continuous linear operator, we said they commute with D, we said they are hypercyclic. So Chan, Hofstad, Walmsley, they show that this is hypercyclic and even has the hypercyclic vector of this form. So this is like they were curious. Okay, now how does hypercyclic vector, or how does what is the form of hypercyclic vector? What is the form of universal vector? And then this was the question we were curious about. Now, if we pick the sequence of composition operators with symbol sigma n, which has the form of a n z plus bn, then what is the form of universal vector by considering C sigma n has those two conditions, which is the universal, which applying the universality, then what is the form of universal vector for the sequence of C sigma n? So this was our question. For a sequence of universal composition operator, is there a universal vector of the following form or not? And even now, this is an open question yet, so we could find just some sufficient conditions, but we haven't solved that in general form. We cannot say all the universal vector have this form. So this was our question. And then we could found these two sufficient conditions. Under the following two sufficient conditions, we can say then we can have a universal vector of the form of infinite product of linear factors. So as you see, this is infinite product of linear factors, and as we know, the infinite product is going to be just the limit of finite product. So the other way we have in the complex analysis, there's gonna be the limit of, for example, j from 1 to mk. Just imagine mk going to infinite. 1 minus z over dj. So we can say it's like approximating the universal vector. So we found this following conditions. Then we said under the following conditions, we can have a universal, the sequence of composition operator, which is universal, can have a universal vector of the desired form of this form. Okay. And this an and bn, because we are working on the sequence of composition operator, from h of c to h of c, this an and bn are just coming from the definition of sigma and of the automorphic expansion. Okay. So the first condition is bn should go to infinite, bn over an should go to infinite. The reason we have these two conditions is because we want to have universality. And we add this to other conditions, and the other condition is 1 over an going to infinite and bn over ln of an goes to infinite. So we want to check now, if we have 1 over an goes to infinite and bn over ln of an goes to infinite, does it satisfy the conditions we should have? Because we now we have universality if for having universality for the composition operator, we should have the slim soup of minimum of this is necessary and the sufficient condition for having universality. So we know the sequence of they showed before in the past the sequence of composition operator under these two conditions I wrote in the red is universal, but they didn't mention how does universal vector look like, as Aniva asked. So what is the form of universal vector? And we wanted to answer this question, so we said under these conditions, under these two sufficient conditions, we found the universal vector can have this following form, which I wrote in the green here. I can circle blue around that. So this is the topic of the question I was working. The universal vector, which have the following form. So now the first condition is clear to see. We have limit soup of minimum of bn, and bn over an goes to infinite. Now for the second one, we want to show under the second conditions we have this one too. So here we have 1 over an. So when we say lim sup of minimum, it's like saying a subsequence that for that subsequence bn goes to infinite, bn over an goes to infinite, bn over an is squared, and a and bn, all of them goes to infinite. So sometimes instead of working with lim sup of minimum, I just, for making easier to say that, I just say limit. So now here we have 1 over an goes to infinite. If 1 over an goes to infinite, it means an is going to 0. And if an is going to 0, when we have logarithmic function like that, so ln of an is going to infinite. Now, because an is going to 0, we know ln of an going to infinite. And on the other hand, we want bn over absolute value of ln of an, we want this goes to the infinite. Because we want this to go to the infinite and denominator is going to infinite, so we know here the numerator should go to infinite, and even is a speed should be more than denominator. Let me show, we can show with this notation. So because an goes to 0 and bn goes to infinite, now you can see you have bn going to infinite and bn over an goes to infinite too. So this was condition we found. Now I want to go through examples to see, so what are, for which type of composition operators we can have a universal vector of the following form. So I want to ask you again questions. So the first example, for example, nz plus n cubed. So this is the question, what do you think? Do you think it satisfies A and B? Do we have for this case is c theta n, do we have universal vector of the following form? Let me ask someone else. Steve, can I? Oh, someone has question. How should I pronounce your now? Your name? Sorry.
Leopold. Sorry,
Leopold.
Leopold. I didn't see you. Okay, I think that Leopold have a question.
Yes. Hello?
Hello, Leopold.
Yes. Good morning, Mrs. Salma.
Nice to see
Thanks
you.
for your kind of presentation.
Thank
I have some question. I want to know if in an metric space xg, if a sequence converge to x, so that that xn is necessary or essential a Cauchy sequence.
Let me to write that. So if we have the space gonna be x,
Yes,
we have the space x. And can you ask
yes,
your question again, please?
yes. If a metric space
So
xg,
we have metric space.
yes,
Then
X,
h of
yes,
g is, oh, we are working on h of g
yes,
instead of h of c. So here g gonna be, for example, a region, yeah? For example,
Um,
You
Yes.
are working on the, so when we say h of g, we mean the space of analytic function on g. You mean instead of h of c, I work with h of g?
Um, I think the question of Leopold was a kind of general question. It
Oh,
was,
general question.
yeah, it was asking whether if you're in a metric space and then you have a sequence that converges, is that sequence gonna be Cauchy?
Oh,
Yeah, and the answer is yes. So there's in a metric space, every sequence that converges is necessary Cauchy.
Yes, I want to know if she considered if it's the supposition or if it's essential for their explanation.
oh, I think you, because we are working with the complete metric space, metrizable space, so every Cauchy sequence is convergent. So we are going to use it. Yeah, I think you're mentioning that. If I'm, did I answer your question? Do you mean that we are using this property?
Uh, okay, good.
Sorry,
Yeah.
uh, please, I would like to know something. Is there any relation with holomorphic function and interfunction? Is it the same? Is it the same space?
Holomorphic function and analytic function, because we are on the complex plane, yeah, they are going to be the same.
In which case, they are not the same.
I don't know on which case they are not the same, but I know on the C they are. Patrick knows this question better.
Yeah, I think we talk about entire function when the function is analytic on the whole plane C, right? So when you are not in C anymore, you cannot talk about entire function. For example, you are working on a domain, a subdomain, right? So you just talk about holomorphic function instead of analytic function, just because it's not on the whole C. So it's
Yeah,
just a kind
So,
of just a
I
matter of
think
appellation, a matter of naming things. Yeah.
I think your question was about analytic and holomorphic. Yeah.
Yeah.
so holomorphic is stronger than analytic.
On entire function, we use that analytic on the C, but holomorphic and analytic, they're different. The definition is a little different, but I'm sure on C they are just the same. Not on this just C, but I'm sure there are some spaces they are not the same, but I don't have example right now. I can check the example and email you later. Patrick, do you know on which spaces analytic and holomorphic are not the same?
Um,
Maybe on D? We had in the complex, I forgot them.
The is a subset
I
of C.
don't have a specific example, but I feel like it's not something very common to like. It should be a very constructive example. Yeah,
Thanks.
because every when a function is holomorphic, it is analytic because being differentiable once in the complex brain gives you the
Yeah.
yeah gives you the
Infinitely many differentiable
infinitely,
and
give you the
continuous.
ability to compute infinitely many different derivatives.
Yeah. Yeah.
So analytic and holomorphic, they are basically the same.
But the definition of holomorphic is different a little, but yeah. They're gonna be this on the C gonna conclude the other one, but it's not in the, I can check that and let you know after that, but thank you. And there is another question. Do the sufficient conditions extend to other spaces of analytic functions beyond? So, ex Gabby asked this question. So the sufficient conditions we found is on the space of analytic function and entire functions. So now we are working on the other space to see what's gonna be. So here we are working the space we have sigma n is a and z plus bn. But if sigma and the space of automorphic gonna be different, so for sure then this sufficient condition is not going to work. Because here the symbols we have, they are coming from automorphisms of C. The symbol sigma and from C to C, they have the form of A and Z plus B. And so if the form of sigma and gonna change, for example, if you are working on the space of H of D instead of H of C, then no, this sufficient conditions we found is not going to work there. Gabby, did I answer your question?
Yes, thank you, Salma.
Welcome. Okay, so then I was here. Okay, so for example, one of the examples when we have nz plus n cubed, and so as you see here, nz plus n cubed bn is going to infinite. If you look at bn over an is going to infinite, and even bn over an squared is going to infinite, and bn an goes to infinite. But if you look at this satisfied, the example we wrote here is satisfy A, so which means you have universal vector of the form of infinite product, infinite linear product, but it doesn't satisfy B. And the reason is if you look at the first one, 1 over A and gonna be 1 over n, that's gonna go to, as n goes to infinite, that goes to 0, but here we have goes to infinite. Let me see if anybody. Oh, someone search something with us. Thank you. Yeah, okay. Then it satisfy A but not B. Now, if we look at to the other example, in this case again, if you look at to the conditions we have in A and B, you can see, I will show the final answer. You can see it satisfies A's because Bn is going to infinite. Again, An is 1 plus 1 over n, so n is going to, let me show here. An 1 plus 1 over n, so as n goes to infinite, this is going to 1, so this is bounded, and bn is n, this is our bn, this is our an. So in this case, you see bn is going to infinite, bn over an is going to infinite for sure, bn over an squared is going to infinite, and bn an going to infinite, but it doesn't satisfy, again, property b, even because the reason is an is bounded, and that is going to 1, so 1 over an gonna be bounded, it doesn't go to infinite. So in this case, anytime theta n has the following form, this is an example that you have the universal element of the infinite product, but here in this example, we show so a and b, they are not equivalent to each other. As you see, this example is satisfy A but not B, which means A and B, from A you cannot say we have B. So it shows our sufficient conditions are independent of each other. Okay. So, and if I want to show a little more of the sequence C theta n, how does it look like from H of C to H of C? So we are working in this case, the first, it means there exists a vector f, which f gonna have the following form. So now f of theta 1, f of theta 2, because when we say c theta n of f n greater than equal 1, I just wrote it to review the operator we are working with. There's gonna be f of the first one, 1 plus, if n is 1, 1 plus 1, which gonna be 2z. If I made a mistake, I will happy if you correct me. Theta 2 gonna be 1 plus, okay, 2z plus 2. Okay, it's gonna be, let me fix it. Okay, the first one gonna be 2z plus 1. Then next, if we combine f by this one, 1.5 or 3 over 2. At the end, there's gonna be the space of h of c. And we know f has the following the infinite product. And the other example is, for example, if we choose theta n of z 1 over e to the nz plus n squared. So again, you can see this time it satisfies b 1 over an because an is 1 over e to the n. So it's clear to see this is our an, this is our bn. So we see bn is going to infinite, but an is going to 0. So as an is going to 0, 1 over an is going to infinite, and bn over ln of an is going to infinite. So it satisfies b, but not a. And the other case, we have this one, theta n 1 over n to the nz plus n. So in this case, again, you can see bn is going to infinite. And this is an. And bn over an, this goes to infinite too. But bn an, if you look at bn an, this is n times 1 over n to the n. So it's going to be n to the 1 minus n. It doesn't go to infinite. Or you can write it as 1 over n to the n minus 1. So this doesn't go to infinite. And if you look at, so it doesn't satisfy property A. And if you look at property B, again, we have an here is going to 0. So 1 over an goes to infinite. But if you look at bn over ln of an, so it's going to be n over ln of n to the negative n, which gonna be n over after getting absolute value. And let me put it in absolute value. And as n goes to infinite, then you see this is not going to infinite. Let me see. Did I make any mistake? Let me check. N over ln of negative n, an, is gonna be n ln of n, and simplify. Here we are going to have ln of n absolute value of n. So as n goes to infinite, ln of n goes to infinite. Yeah, this doesn't go to infinite. Okay, it doesn't want me to write. So this was the sufficient conditions we found. And then to prove our main result, we introduce a property, then we use that property to show the correlates. So for example, one of the correlates we found, so you see different examples here. And in the examples, you can see in some of examples, like here, n is going to 0. So based on the examples we had, so we have this idea. Now, if we make an bounded and bn goes to infinite, so for sure we can have universality, and we might have the universal vector of the following form. So this was one of the correlates we had. So we showed that under the following conditions, like a generalization of our examples, under the following conditions, we can have a universal vector of the following form. So before going further, I want to see how much do I have time. Gabby asked a questions, so let me answer the questions.
Salma,
Steve, how much do I have time?
normally,
Not much time.
Not much time, so I cannot go through the proofs. So let's answer the
Salma, I have a question.
Oh, good.
I have a suggestion. If we try, for example, AL equal to 1 over n
Can I
and
write your
bn,
question? Let me write. I need the, okay, I need a place to write it. Okay, if I have
AN equal
AN,
1
mm-hmm,
over N
mm-hmm,
and BN
BN,
N cubed
N, okay,
N cubed.
N cubed. Yeah.
Single.
So the question is, do we have universal vector of the following form?
Yes.
That's nice. Let me check. So 1 over an as n goes to infinity, this is going to 0 and bn is going to infinite. So first of all, bn goes to infinite and we like to have this condition. And bn over, I don't know why it's coming each time. Okay. And bn over an, the absolute value of bn over an is gonna be n cubed over an, let's say just multiply by reciprocal of an. So it's gonna be n to the 4, yeah? This is going to infinite. So for sure we have universality. Thank you. So now let's check, do we have universal vector of the following form? So for us, bn goes to infinite, bn over an goes to infinite, and bn over an squared is going to infinite, and an bn goes to infinite too. So this satisfies condition A. So for sure I can say we have the universal vector of the following form, f of z, the product of I from 1 to infinite, 1 minus z over di. So we can have a universal vector of this form. But Steve, but I cannot answer your question of this form. But if you give me something that doesn't satisfy n and a and b, then I couldn't answer your question. So I just could find these two sufficient conditions, that under these two sufficient conditions, we have a universal vector of this form. But this is an ongoing research, so I don't know if you give me something like this, like do we have like the last one, which was here, yeah. But if you tell me about this one, do we have universal vector of the infinite product form? Then I don't know. We have to see if that works or not. So we don't know for all cases yet. Did I answer your questions? Oh, sorry, someone else. Oh, yeah. So let's answer this question. Is there an intuitive or geometric interpretation of universal vectors for composition operators on the complex plane? Uh, Gabby, the intuitive I can show you by the picture. By geometric interpretation, I can give you analysis interpretation, but I don't know what you mean exactly by geometric interpretation. I'm reading the chat. Does this mean that for real space, it would depend on differentiability? And for real space, by the real space, what do you mean by the real space? I cannot pronounce your name. It's a little tough for me. Is that FUS? How should I pronounce it?
I
Patrick,
think you can say Cyril, right? There's a syllable.
Cyril. Okay.
Well, I'm talking about what about if you're in a race space? If you're in a race space, uh, holomorphic function are necessary analytic, or it will depend on the differentiability.
You mean the space of holomorphic functions?
Oh,
So, yeah, Patrick, you wanted to say something?
yeah, so I think maybe this comes from the fact that we were talking about holomorphic and analytic, and we're saying that, okay, if you are on the complex plane, holomorphic and analytic are the same. Now the question is, if you're on the real space, are they still gonna be the same? And the answer is gonna be no. Okay, because in the real space, holomorphic is similar to differentiability, and then analytic is similar to infinite differentiability. And a function being one differentiable, like differentiable only one time, like a C1 function, is not the same as being infinitely many times differentiable. But in the complex plane, every time something is differentiable once, it's going to be differentiable infinitely many times. But in the real space, it doesn't work that way. So that's why sometimes it's very nice to work with complex functions that are defined on complex spaces, because you have that differentiability for free, that infinitely many differentiability for free after the first derivative. And I don't think differentiability actually matter a lot in your work, right? Because you're not differentiating any function, just using some compositions.
Yeah, so differentiability on the space of, because we are working on the space of analytic functions, it gives us the space we are working with that. If it wasn't h of c, it wasn't easy to work with it. So we are using that, but it's like hidden inside the concepts like that. But as Patrick said, when we have this, for example, there are many theorems that we have for the space of analytic functions on C, but if you change C to the R, they are not going to work. Yeah. Thank you,
This
Patrick.
will mean that it will be the Taylor series will mostly be zero.
The question was, does it mean that the Taylor series are always gonna be zero then? And I think the answer is no.
What was the question? I couldn't hear the question.
The question is, okay, if you are on the real space, does it mean that the Taylor series are going to be zero if we don't have if we don't have that the function is analytic? And I don't know if I got the question right, but if that's exactly the question you asked, the answer is no. Yeah. Because saying that the function is not differentiable doesn't mean that, okay, the function is going to be differentiable and the derivative is going to be zero. So the function is not differentiable means that it's not differentiable. So we cannot even talk about Taylor series. So you can't even have the terms of the Taylor series in order to say they are going to be zero. So
For example,
what I'm talking
yeah, for
about
example,
is when I'm talking about building a Taylor series of that function at x equals zero, that is what I mean. It means the Taylor series will be zero. That is what I mean.
the function of the Taylor series being zero? I couldn't follow the question.
Sorry, I didn't get that right.
Can you repeat
Okay,
again? Sorry.
when we use space,
Mm.
my first question was that if you're in a real space, will holomorphic function an analytic function be the same? If no, and then would it depend only on differentiability? He said he was explaining to me that it not there are other factors, and what I'm also I want to increase is that if you want to build now a Taylor series, would a Taylor at the function of a function at x equals zero, the Taylor series will be zero. It means that it will stand at zero.
You're asking if the Taylor series is zero, it means we expanded at zeros?
Could you say that in French, and then maybe I will try to say it.
What I'm saying is that in a real space, if you want to build, you said I said when I was asking holomorphic function, are they the same in to analytic function in Uri space? It's no. Then if you want to build a Taylor series at x equals 0, my question is that will it converge to 0?
Oh,
So
so will the Taylor series at 0 converge to 0? That's the question. If you're on the real space.
are you
Yeah.
talking about the Taylor series done on the real space?
Yeah.
And the question is if the Taylor series f of z is equal 0, what was the conclusion?
The question was if we are writing the Taylor series of a function that is defined on a real space at 0,
Oh, the Taylor
is
series around 0, b0, okay?
is the Taylor series gonna be 0
For any function
for any
that
function?
you can. Yeah.
It doesn't need to
Yeah,
be 0.
yeah, it doesn't need to be 0. I I think maybe you're thinking about that because maybe you see analytic function as an times z to the n, right? That's not the general form of analytic function. The general form is an times z minus, right? As
Yeah, that is what I'm talking about. Z minus 0. That is exactly what I'm talking about.
yeah. So and then if you have that expression, then it doesn't go necessarily to 0. It will depend on the coefficient an's and probably
Yeah,
where z is.
yeah. It depends on the conversion. Could Patrick answer your question? I was silent, so.
Okay. Thanks.
But it was nice question. It was nice talk. Let me see the other question. Is there any link between condition A and B since both them help to conclude the same result? Do you mean we can conclude from one of them on another one by having any link between them?
No, like you state two conditions which are condition B that are sufficient um, to conclude that the function there is universality.
Mm-hmm.
So since both of them had to conclude about universality, I was like, is there any link between them? Like what is any entry like
I don't know, is my internet or your
no
internet? I could hear your voice till you said because A and B, both of them, they are given universality. Then I couldn't hear the rest of your voice. I don't know if it was my internet or your
yes,
internet.
no, my internet I think. Since both of
Ah,
them had to conclude about universality, I wanted to know if there is a link between them. Like maybe the link will come to the proof. There,
oh,
there are two
the,
sufficient conditions, but are there any link between these two different conditions?
they are independent of each other, but both of them, they are just satisfying this condition and Bn over An goes to infinite. This is what both of them they are satisfying. Bn and Bn over An goes to infinite, and we need it to have universality. But as you see in the examples, we can have some conditions they satisfy A but not B, and there are some conditions they satisfy B but not A. But even the way we were constructing the universal vectors, so it was a little bit different. It's not, they are completely different, but both of them, they are the same in satisfying Bn and Bn over An goes to infinite.
Okay, okay. Thank you.
Thank you. And there is another email. Uh, Gabby, you wrote something. I was thinking about this. Do you want to ask your question? It was imagine. I can read it. So I was thinking about Gabby. I was thinking about a simple analogy. Imagine having a special brush by repeating the same type of brush stroke many times. You could eventually reproduce almost any painting in a similar way. Yeah, I think it's gonna be very close. If I understand correctly, starting from a single function and repeatedly applying a composition operator, we can approximate many functions in the space. Yeah, we can approximate almost all functions in the space. You're right. It's not even many, it's almost all functions in the space. That's right, Gabby. That's nice. So, and Samuel shared with us the function is holomorphic on an open set if it is complex differentiable at every point in the set, and he shared a function is analytic if for every point in its domain it can be represented by a power series that converges within some disk. And there are other definitions too, Samuel, they are similar to that. I think you shared with us there, but thank you. So thank you everybody. Sorry I jumped into asking questions because we cannot have time to go through the proof of the theorems and the corollaries, and I will bring the reference. This was a part of the work of me and my professor. We have submitted, it's under review, it hasn't been published yet, so thank you everyone. Any other question, I will appreciate it. Thank you. Any
Okay,
question?
thank you very much, Salma, for your very nice presentation.
Thank
Okay,
you.
since there were already have many questions during the presentation, if anyone have a short question, you can take now. Okay, I think Samuel and Raul have the question. Okay, we can start by Raul. Raul, you have the floor.
Okay, thank you for your nice presentation.
Thank you.
I have two questions. Okay, my question is regarding your topic. What has already been accomplished and what do you plan to push in the future?
In the future.
Yeah.
So, so the first of all, this is we just found two sufficient conditions, so the question is somehow open yet. So as for example, we want to see can we have this kind of universal vector always or not, or just under this two conditions, or what are the other sufficient conditions we can found? Is that sufficient and can we found any sufficient necessary conditions? And the other things I'm interested in is if we change the space from h of c to another space to h of g. So now we are working with the space of analytic function on C. What about if instead of G we had, for example, I don't know, D, or we had infinitely many space, a region with infinitely many holes? This is one of my favorite questions. I'm working on that, which on the space of analytic function on G, where G has infinitely many holes. So I mean like this if I want to answer. So we know when we talk G, a region, open set, so just now consider instead of working with C, if this is C. So let me. So imagine I 0, sorry, 1, 2, -1, -2. So what about if I have infinitely many holes in C? Then how does look like the universal element there? Can I say the universal element have the same uh the same form like infinite product or not. So there are a lot of questions we can ask. We can change G and put different conditions, and we can say, okay, under these conditions, do we have a universal vector of this form or not? Or you can say, okay, what about you can search for the other universal element. So this is just one of them because we know the set of universal element is dense in the space of H of C. So for sure you can find, I think in this way, we can find the universal element which has the different form from what I'm introducing. Did
Okay,
I answer
thank
your
you.
question, Raul?
Okay, thank you.
Okay. And Samuel has question too.
Okay, we have the question of Samuel. Samuel, you have the floor.
Okay, thank you, Salma, for being with us during this Café Scientifique. My question is not a specific question, but I would like to know if in your exploration, do you use some algebraic properties of interior functions? Or of analytic functions, because the set of those entire functions form a ring. It can also be, it is which kind of ring? It can be an integral domain, it can be a Bezout ring, but it is not Noetherian. I don't know if those kind of algebraic properties of this space or of this ring you are working on may help you to, I don't know, may help you to push forward this study you're working on. I don't know. So because when I'm working on some structures, I need to find what are those properties, how those element functions, how those element behave. I don't know if you make those kind of exploration within your thesis.
So for me, because I had to construct a universal vector, so I was using the form, how, for example, the analytic functions are. I was using a lot of theorems in the complex analysis because I wanted to have a infinite product, but I wanted to be convergent at the same time. So I was using a lot of complex analysis and a lot of the structure there, but about the to use the rings properties or that kind of properties, I wasn't using them, but it will be nice, I think, if someone wants to extend it to instead of working on H of C, how does it work for the semi-group on the semi-groups? Because I know my professor had worked on the semi-group instead of working H of C or H of G. And they might be, I don't know, maybe they could conclude from that this result too, but I wasn't working in that area, but it was nice to mention that. I wasn't working in that area, yeah.
Okay, that's fine. And thank
Thank
you
you.
once more for being with us.
Thank you, Samuel. Thank you for nice question. I will think on that. I will think on how can I use more algebraic properties in here. Or maybe I could extend it to semi-groups, but I wasn't doing that here.
Okay.
There are another question.
Yeah. Leopold?
Okay, Leopold, you have the floor. Leopold, you have the floor.
Yeah. Thank you, Steve, for another time. Mrs. Salma, I want to know what is an economic application, direct economic application of using on complex plan, the composition operator in universal vector.
I don't know about economic application of that. It's pure mathematic. So I have no idea about that. I don't know to be honest, but I know, for example, what I'm working is universality for the composition. I'm working on is like dynamic of linear operators, but I know we have dynamic of nonlinear operators, and we can see, I think, applied mathematics or maybe application of this maybe in that area, but I don't know about what's gonna be the application of this. I don't know, to be honest. I'm just doing that because I'm enjoying to be too much abstract.
Okay, thanks.
Maybe we should ask Patrick this question. Patrick, do you know the application of or the economic application of your work? Because you are going to work on the same area.
I don't.
You don't. We just do it because we enjoy math, pure mathematics. I think in this way, I don't know. But it was a good question. I have to think on that. I don't know.
I'm economics. I usually think about the application of mathematics on the real life, on social science.
That's nice. Here we
Yeah.
are, for example, for hypercyclicity, we are working on the space of infinite dimensional. I don't know how should I consider a space of infinite dimensional on the real world. What's going to be the infinite dimensional? Patrick, can you give us some examples of the space of infinite dimensional in the real world? Infinite dimensional space. I don't know. Do we have infinite dimensional space?
Uh, I don't know. I don't think so. I think the best we can comprehend is three-dimensional, right? The
think
spatial dimension and the time. But I don't know much. But I don't know how we can apply hypercyclicity or universality in real life. But we used to say this for some mathematics that we are applying now, and maybe in the future we're gonna get some application. So that's not especially the role of mathematicians, like I mean pure mathematician. We just develop mathematical theory, and we just hope that okay, in the near future maybe some things are gonna pop up, and then these mathematics are gonna be useful. For example, right now, linear algebra is something that is extremely useful in machine learning. And back then, we didn't know that, oh, this is gonna be something that's gonna be useful. We were just doing math because it was math, right? Just pure math. And hopefully, we get some application of these things in its own future.
we hope.
Yeah, we hope.
Mostly, I think it's in spectral analysis because mostly the infinite dimensional space are used in analyzing songs. They're just concepts. They are not real, but they are they are good for sound analysis, like using Fourier analysis and others. That's where I think mixture analysis are mostly used for application in real life. But it will be possible from a theoretical background working from now to extend it for predictive journalism based on this on if I want to, because I wanted to apply the Feynman diagram to sociology by using by viewing particles as a social event and interactions. So, mean that when interaction with a particle as a social event, and each the graph will be be showing the dynamics, because for it to function, we need to have the barrier for now for it to function is that we need to have enough data, enough big data. The big data that we have is not yet sufficient, and I'm not sure the technology is is um, is up to date.
That's cool. I think that is cool to use it. And that's why.
Okay. No more questions.
I think that is Sirira's microphone problem.
Yeah. Someone's microphone has problem.
Steve, if you are talking, we cannot hear you.
Steve, can you open your microphone before talking?
Now it is good. Hello.
We can hear you now.
Okay. Sorry. I said that we can stop the meeting if there are not another question. Okay. Thank you very much, Salma, for your presentation, and thank you again for accepting our invitation. Thank you all for your presence this night. Sorry, and see you next week for the next Cafe Scientific on P.
Thank you, everybody.
Thank you. Thank you.
Okay, thank you.